Now let's take a deeper dive into the ins and outs of the actual thermal analysis process using SimCenter FlowEFD. We have our simplified model which we've added detailed PCB and IC component information to. This simplified model runs quickly and can be used as an early stage conceptual simulation before design commits occur. We can show the computational domain which is sized around the assembly. This is a natural convection case with a larger domain in the Y direction to capture the heat plume. The FlowEFD check geometry feature correctly identifies the fluid region, so we're ready to start the analysis. Taking a look in the general settings, we can see fluid flow and conduction is enabled along with gravity in the negative Y direction. Air is our only working fluid. The default material is set to aluminum 5052. Our initial conditions are atmospheric pressure conditions at sea level with an ambient temperature of 20 degrees C. The FlowEFD ribbon toolbar has all of the pre-processing features which can be applied to the geometry. We can check these by clicking through the FlowEFD analysis tree. Aluminum is applied to the heatsink and polycarbonate is applied to the fan. The fan itself has a fan boundary condition, which is the manufacturer PQ curve defined in the engineering database. There is a contact resistance on the underside of the heatsink to represent the thermal pad. The DDR RAM modules are modeled as two resistor components which were imported from the FlowEDA bridge. We can confirm the heat load and the temperatures once the solver has finished. Finally, there are some FlowEFD goals which are monitoring key numerical values such as component temperature and fan flow rate. If we zoom in on our Ethernet controller which we calibrated, we can open the assembly and confirm there is a FlowEFD sub-project associated with it. All materials, resistances and heat loads from the Trista calibration are present and correctly defined. A very powerful FlowEFD feature is the ability for the parent assembly to inherit sub-assembly project definitions. This is done through the Add from Components feature, which scans all NX components for a previously defined FlowEFD project. In this instance, we're interested in importing the PCB, the calibrated LQFP, and the U1 BGA component. These have been previously imported and the green checkmark confirms this. We can check the imported FlowEFD features by expanding the tree and showing the PCB, for example. The thermal conductivity with the averaged approach is being used, and by zooming into the LQFP, we can see the IC is correctly sitting on the PCB pads. Let's now discuss the FlowEFD computational mesh. FlowEFD uses a finite volume immersed boundary Cartesian mesh. The manual mesh mode allows the user to define the XYZ base mesh size, which is 16 mm in this case. The user then defines a slider bar level which controls how many times a base mesh cell can be octary split to capture the geometry. We can see the channel refinement is set to 5 while all other sliders are set to 4. We'll come back to what this means shortly. Once the mesh is set, we can run the mesher and solver, which can utilize multiple cores by default. Looking at the mesh, we can see the entire assembly colored by mesh refinement level. Dark blue level 0 cells are the 16 mm size we defined. Light blue level 1 cells are 8 mm, and so on. Zooming into the LQFP, we can see red level 6 cells which are 0.2 mm in size. This is because the LQFP sub-project has a finer mesh level defined. The heatsink has orange 0.5 mm cells applied, which is the maximum project mesh level. Looking at the results, we can see the entire assembly colored by temperature. We can probe the temperature at the mouse position. Individual parts can also be focused on, such as the heatsink. As we know, the PCB is a critical heat flow path, and we can see that the RAM modules are getting hotter than the FPGA itself. As the PCB is a thermal resistance matrix, we can report the temperature within the board and check individual layers for where the hotspots are. We can see a roughly 76 C zone under the RAM modules, which is well within acceptable limits. We can check internal layers to ensure good heat conduction and feed back this data to the ECAD team, as high temperatures can affect power and signal delivery. The airflow can be visualized and animated, such as the flow through the heatsink colored by fluid temperature. Slices through the model can be taken to show internal temperatures. We can see the FPGA junction temperature is 81°C, then a lower temp in the heatsink, which is due to the thermal pad resistance. Cut plots can also show fluid velocity and other parameters. Finally, the goal plot gives us the numerical values of the critical parameters from the simulation. The U1 FPGA junction, RAM modules, and Ethernet controller temperatures are reported. The fan flow rate and PCB temperature is also shown. Okay, now we've looked at the simplified model, let's bring back all the suppressed components for a late-stage validation simulation. The FlowEFD project doesn't have to be scrapped and restarted. The project clone command is all that's needed. The mesher is run again, and we can see the vastly more complex mesh now. The maximum refinement level is still 6 with the finer mesh on the LQFP. The surface temperature plot now includes all the previously suppressed components. We can quickly report the hottest RAM module temperatures using the callout. The flow is much the same, with perhaps some earlier separation due to components deflecting the flow along the PCB. We can compare the results between the simple and detailed modeling levels using the Project Compare tool. We'll compare the numerical goal values, which can be seen in the table. Interestingly, the U1 FPGA temperature is 4.5°C hotter on the detailed model. Most of the other components are within a few degrees, however, and the fan flow rate is almost identical. The simplified model runs faster with fewer PC resources, which is why it's useful to have as an early-stage upfront simulation model which can then be iterated on. We're on the home stretch. Let's put it all together in the top level assembly we saw a peek of at the very start. The PCB assembly we've been working on is one of many within our electronics product. There are other PCBs, vent holes, radial blowers, and axial fans in the master assembly to consider. The FlowEFD thermal analysis process is ostensibly the same. The computational domain size is defined and can be seen. The sub-assembly FlowEFD projects are all inherited by the top-level assembly, so no individual boundary conditions need be applied. This makes the project very modular if we need to use any of these PCBs in a future product. The mesh is significantly larger and the runtime proportionally so. Once complete, we can see the cut plot slices through the model, showing air velocity and temperature. The flow trajectories show the airflow path through the chassis. The inlet vent on the bottom is sucking air and passing it through to the radial blowers. There is a distinct recirculation zone around our SC100 control board at the back of the enclosure. What we've seen is the modular nature of FlowEFD projects, which stay connected to the CAD and can evolve as the product matures. This streamlined, data-managed thermal analysis process makes staying on top of thermals very straightforward and intuitive.